Hello and welcome to the Project Robotic Rescuer Briefing. I am George Hood, and it is a pleasure to be speaking to you today about this exciting technology. We began this effort by asking ourselves how we could best help our military on the battlefield of the future, and we answered that question by crafting this problem statement. Reaching casualties in highly lethal battlefield areas may be difficult. The modern battlefield is the most lethal combat area that American forces have ever faced. The volume of precisely aimed fire as well as guided munitions guarantee that large numbers of casualties will occur, and that reaching many of those casualties in fluid battlefield conditions under fire may prove difficult. Robotic units can augment the frontline medical providers. Robotic units, search and rescue units, are not meant to replace frontline medical providers, but rather to augment their capabilities under circumstances where those providers cannot safely reach their patients. Robots have a role in combat medicine and combat search and rescue, but there are presently no robotic systems being utilized. Unfortunately, while there is a clear need for robotic technology on the battlefield and in search and rescue operations generally, there are presently no systems being manufactured or deployed that have the capabilities of Project Robotic Rescuer. Our units can locate casualties under fire, enter denied or high-risk areas with medical assistance and supplies, and extract a casualty. Our buyer is the U.S. military. Our end users are military personnel assigned to medical and search rescue units. Our stakeholders are our investors and stockholders, the Department of Defense, and the U.S. Congress. Briefly, our design requirements are survivability, ability to communicate, ability to allow medical personnel to assist a patient in the field, video capability, ability to carry emergency supplies, ability to carry medical supplies, capability to be remotely operated, capability to be operated for 24 hours before requiring recharging or refueling, capability to carry a complete sensor array. Lastly, the units must be camouflaged. Our team of 4 robots consists of a casualty locator, an obstacle defeater, a medical provider, and a casualty transporter. Thank you. We will now begin the presentations of the individual robots. First up is Cody Wynn.
Okay, thank you for that introduction, George. My name is Cody Wynn, and I will be demonstrating the first robot of our swarm system, the casualty locator robot. So the first thing I'm going to show is the mechanical design. As you see, the overall design of this robot is kind of a quadcopter design, fairly standard. The material is going to be made out of fiberglass in order to keep it strong but very light. And the different components of the device you can see highlighted in this image below. The overall size is going to be about 36 inches across by 12 inches tall. There are going to be 4 DC motors that drive the 4 propellers to keep it aloft. And the pitch of those motors is going to be controlled by 4 servo motors inside of each of the arms. On the inside, there's also a battery to provide power, an Arduino board to give it the brains and the logic. And on the underside, there's a temperature sensor, aka a thermal sensor, and a light sensor, aka a camera, that it would be scanning for casualties and obstacles in the way of the search path. And you can see on the right here, just a quick demonstration of how the pitch will be controlled by the servo motors inside of the arms. So here's a look at the circuit diagram showing you some of the internals for the electronics. We have on the lower right here 4 DC motors controlling the propellers. They are wired in parallel, so they all go at the same speed, but their speeds are controlled by the logic of the Arduino board, controlling the voltage to a transistor that controls the power from the battery. So that's what controls the RPMs of the propellers. Each of the pitches is controlled by an individual servo motor that can help, 2 at a time will turn in order to make it turn left or right, or all 4 will lean forward in order to make the unit move forward. The sensors you can see on the left side here, this upper left one is the camera sensor, which is used for detecting obstacles. And this temperature sensor here is used for detecting casualties. So it can see fairly well through the any kind of foliage or rough terrain background. The logic of the unit, essentially our system is controlled by a central hub unit. That central hub will receive and then transmit a command to this robot, this locator robot, to take off and follow along a set search path set by the central hub. So when the robot receives the search path commands, it will take off and begin flying through the air along a designated flight path. While it is flying, it will be continuously searching for obstacles and casualties. If it finds an obstacle, it will transmit the location to the hub and then continue along its flight path. Its primary objective is to find a casualty. If it finds a casualty, it will transmit the location of the casualty, and then it will circle around the casualty continuously until it receives further instruction from the central hub. So now I'm going to cut real quick to the 3D design of the robot. So you can see essentially what I showed in the earlier presentation slide, but what I wanted to demonstrate here was the angles. So when the propellers need to provide either forward movements or turning, they will move forward at a 30-degree angle. 2 of them will do it to make it turn one direction, and all 4 will move forward in order to make it lean forward at an angle like this. If I make the unit transparent, you can see the internals. with the Arduino board, the battery, the 4 servos, and the DC motors are inside of these housings. And then if I jump over to my circuit design, this is the circuit as I showed. I will put it into a simulation mode. I won't go into the detail, though. Right now, the unit is under power. The servos are at a 0-degree angle, and the motors are at 0 RPMs. If the central hub gives it a command such as take off, see there will be about a surge of speed in the motors. So they would jump up to about 3,800 RPM. And once it reaches a cruising altitude, it will settle down at about 2,400 RPM. If the unit needs to move forward, it will receive a forward command. All 4 of the servo motors you can see pitch forward at 30 degrees for a few seconds to give it some forward momentum, and they return to 0, and it will continue that process as necessary. If it needs to move higher, the RPMs of the servos or the DC motors will surge for a while, and then before returning back to cruising speed. And if it needs to move lower, they will slow down a little bit. Similarly, I can turn left. 2 of the servo motors will function and return, and turn right to go in the opposite direction. Now, over on the left side, I'll demonstrate the function of the sensors. So the camera sensor here, which is pre-programmed with an algorithm in the Arduino board to search for different types of obstacles. But once it finds something and receives a certain input from the terrain, you can see in the serial window monitor down here, it'll identify an obstacle was found, shares the obstacle with the hub, the location of it, and then it resumes its search path. Similarly, the temperature sensor normally reads about an ambient temperature as it's scanning. When it identifies a temperature scan that is close to human body temperature, it will identify that a casualty was found, share the location with the hub, and begin circling the casualty location. And you can see over here, 2 of the servo motors are pitched forward to provide it that circular path. So you can see the rest of the code that will be provided in the slides after the presentation. But for now, I will pass along the presentation to Monik, who will do the presentation of the obstacle defeater robot that will respond to the obstacles found by the search robot.
The swarm's second robot, the obstacle defeater, will be responsible for removing obstacles when encountered by the Pathfinder. The robot will be about 22 inches in both height and width, and 75 inches in total expanded length. The design will consist of primarily 2 object moving mechanisms. On the flat backside will be a barrier pushing plate that is extended from the robot using a push arm. The pushing mechanism will consist of a motor and a gearbox that will increase the torque, and a force sensor that will determine if the obstacle is stuck on the pushing plate. On the slanted front surface will be an inflatable high pressure balloon that is ejected from the cone-shaped nozzle. The robot will be driven by 2 motors on continuous steel tracks, which will increase stability and maneuverability for rugged terrain. And the motor will consist of, in total, 2 sensors, a distance and a force sensor, and 4 actuators, which includes 2 drive motors, a compressor for the balloon, and a push motor for the push plate. The following is the circuit design, which models the 2 sensors and the 4 actuators. The 2 sensors included are the distance and the force sensors, and the 4 actuators are the 2 drive motors, and the push plate is represented using the servo, while the compressor, the air compressor, is represented using the light bulb. The robot will receive GPS coordinates to the obstacle from the central hub, and will begin moving towards the coordinates along the swarm path until it hits the obstacle with the force sensor. When the force sensor detects a obstacle in which the force sensor will be high, it will begin to extend the barrier push plate as it pushes the obstacle. If the push plate is successfully expanded all the way, that means that the obstacle has been moved, and the robot will send a message to the central hub, letting it know that the obstacle was moved. If the push plate was not successfully moved, the robot will turn 180 degrees, allowing the other mechanism to be used. It will inflate the balloon, dozer, and it will then use the distance sensor to determine if the obstacle was successfully moved. So this is the working model of the robot circuit. The first thing that the robot does is await the coordinates from the central hub to the obstacle. It then uses those coordinates to traverse the path and make turns as necessary. This is simulated in this model by sending an input from the serial monitor. So if the robot needs to move forward in order to get to the coordinates, both of these motors will move in the same direction in order to move the robot forward. So in this case, the central hub has sent the command, and now both motors are moving in the same direction and the robot is moving forward. In order to turn the robot, one of the motors will need to move in the reverse direction. Now the robot is going to stay in motion and keep traveling along the path until it comes across an obstacle. The obstacle is sensed by this force sensor. Currently, the force sensor reads 0, so the robot drive motors will keep spinning until the sensor detects a force. When an obstacle is detected, the push plate is going to push the obstacle, which is indicated by this servo. So now that the obstacle is detected by the force sensor, the servo has now turned 90 degrees, indicating that the push plate has expanded. As the push plate pushes against the obstacle, there will be an increasing force acting on it. So this force sensor, as this push plate opens, will continue to go up. If the push plate is able to fully expand, that means that the obstacle is successfully moved, and the robot informs the central hub. But if the force sensor on the push plate exceeds the maximum limit, which in this model is 5 newtons, the push plate will collapse. So when this force sensor increases above 5, the push plate collapses, and the servo returns back to its low state. This returns the force sensor value back to 0. The robot turns 180 degrees, which you can see by the motors in motion. After it has turned 180 degrees, the motors will stop rotating, which now they are at 0 RPM. And the air compressor will turn on in order to inflate the balloon, which is indicated by this glowing light. So now that the light is on, that means that the balloon has been inflated and is pushing against the obstacle. Finally, the proximity sensor will be used to determine whether the inflation balloon was able to successfully move the obstacle out of the way. If the proximity sensor determines that the obstacle has moved greater than 75 inches, that means that the obstacle has been successfully moved, and it will send a command to the central hub. So in this case, the proximity sensor reads that the obstacle is at 102.5 inches, and so it sends the command that the obstacle has moved.
Hello, my name is George Hood. Welcome to the briefing on Robot 3, the medical provider robot. This robot has evolved substantially throughout development, and it is much larger and more robust than it was at the first design shown here. This is the final design. The colors shown are not the ones that will be used in the production robot. Use of colors here is simply for illustrative purposes. The most significant changes are size. This unit is about 3 times larger than the original design. On-ground mobility, this unit sports a completely redesigned drive system, incorporating large all-terrain tires, independently steered axles, independently suspended wheels, and 8 inches of ground clearance. Airborne propulsion, this unit has larger propeller systems, better positioned for more lift. Here's a rear view showing some of the dimensions. The width of this unit is the same as the width of the original design. It is about 6 inches higher than the original. The real change is in the length. These are the changes from the original design. This final design is almost 3 times as long as the original unit, allowing it to carry larger and bigger loads of not only emergency supplies like water, food, and medicine, but also larger items such as weapons and munitions. Here we see the inner workings of the robot with the cover removed. Shown here are the logic board and a motor servo unit. Let's look at the robot's Arduino board and circuitry. At the top left, we see the drive motor in yellow. Immediately to its right is the proximity sensor board with its sending and receiving units. At the lower left is the Arduino board with its onboard processor. On the right is a circuit board with an L293D motor controller. At the bottom is the power supply. The proximity sensor, which would be this item up here, continually sends and receives echoes. The Arduino calculates the distance to the object and then determines, based on the coding, whether to advance or stop the robot. Motor current is controlled by the motor controller. When an object is within 15 inches of the sensor, the Arduino sends a signal to the motor controller and it stops current flow. If there's 15 or more inches of clear space ahead, the motor controller will continue to supply current to the motor and the robot will advance. Here's a flow chart showing how all that works. At the beginning or at the start, the robot is already deployed on the ground. It advances and until it encounters an object. If the object is within 15 inches, it stops and waits for a steering command, sending a query to the steering for a steering command from the hub. When the hub responds, then it begins to drive again. If there was no object within 15 inches, it continued to drive. Again, coming around to the next, and this loop, by the way, will then feed into this loop. If the next object is within 15 inches, it will then proceed this way. If it's not, it will go right back and this loop will run continuously. If the object is within 15 inches, then we have a query being sent for GPS data to the hub. And if it is in fact at the same location, then in other words, we have arrived at the casualty, we stop and wait for instructions. If the GPS data is not equal or equivalent, then we stop and wait for steering commands. We send a query to the hub responds, and we go right back and start the loop again. This is the code that makes it happen. I would just point out that we have commands received here from the central hub, and we have a simulation of this robot. Stand by. Here is the proximity sensor. If it's at, and you can see the serial monitor operating down here. As soon as it goes underneath the green zone, which is 15 inches, we are then at a stop condition. When we exceed 15 inches, the motors begin to advance and commands are received, steering commands are received, and it continues to execute those commands. And that concludes my demonstration and my presentation. Thank you very much. I will be followed by Cody Wynn, who will do the summary.
Okay, thank you again, George. Pardon me while I scroll down. One thing we do want to include, as outlined in the previous slides, there are 4 robots in this package, this system that we have designed. The 4th robot is the casualty transporter robot. Now, we don't have Joshua Myers here, unfortunately, to help us present this, but I did want to give just a brief overview of what the design was intended to look like. Essentially, it's a moving bed to help transport the casualty away along the path that is provided by the central hub and cleared by the obstacle robot. Then, speaking of that central hub, I want to go over really quickly the logic of the central hub. Now, there's a lot of more detailed logic that would occur in the background, but this is kind of an overview. So the central hub would receive a request for help from any source, whether that be a casualty on the field or intelligence or whatever. It will deploy the casualty locator robot to the set search area, and this is where it continues to work with that robot to give it its coordinates and its path while it's waiting for the feedback from the casualty robot. If it receives an obstacle location, it will share that obstacle location with the obstacle defeater robot and deploy that robot. And then we'll continue waiting until it identifies the casualty location. And once the casualty location is identified, the central hub will share coordinates and deploy the medical provider robot. And then also following after that, the casualty transporter robot. So, being that this is a presentation to try to go over to sell this system, I won't go into the details of all the numbers here presented, but we did do the research. And I just want to highlight this number on the top right. The overall cost of the system is $235,000, which is, in our opinion, more than reasonable for a system with capabilities such as this. We also want to emphasize that this type of technology is revolutionary in this field. Robots are ideal for hazardous situations such as the modern battlefields or any other search and rescue operation. And this is a great opportunity for any investor because a system such as this can help save the lives of casualties without risking the lives of rescue personnel. And the swarm structure is much more capable and adaptable than any other system that's currently on the market. And finally, to summarize, the central purpose of this system is search and rescue. 4 robots have been designed in order to achieve that goal: the casualty locator, obstacle defeater, medical provider, and casualty transporter. This is an autonomous, safe system that can reach remote, hard to reach, dangerous areas such as battlefields. Could potentially be adapted to other types of search and rescue, such as injured hikers or disaster response. So finally, we just want to say thank you for your time. We hope that we were able to demonstrate the value of this system and that we were able to convince you to invest in such a system. Thank you very much.